these next examples, we're going to draw graphs to model certain problem scenarios. So in this first example, it says the Navy Region Southwest, or NRS, is a division of the United States Navy. NRS includes all Navy facilities in the states shown in the figure. We're going to construct a graph to show the states that share a common border. States whose borders touch only at a single corner point will not be considered to share a common border. So for instance, right here where these four states meet each other, that won't be considered to be a common border. This is actually called the Four Corners, and it's a pretty popular spot. If you're looking for an idea of where to go on your next vacation, this would be an awesome place to go check out in the United States. Okay, but in any case, let's go ahead and construct a graph to show what's going on in this. Alright, so each one of these states is going to be boiled down to just being a vertex. So I'm going to have a vertex for California, which I'm going to use the state's abbreviation, so CA. And then, if left to my own devices, I sometimes like to put my vertices in the kind of same spatial orientation as it exists in the original picture. Okay, so it seems like kind of going across the top here. I've got California, Nevada, Utah, and Colorado, and then down here I'll have Arizona, and then New Mexico. Now when you're making your vertices, make sure that they are large enough to be able to be noticed, but maybe not too large that it gets kind of carried away from you. Okay, so I have my 6 states all represented by a vertex, so then if they have a common border, we're going to draw an edge connecting them. So for instance, California and Nevada share this border right here, so I'm going to draw an edge connecting them. California also has a border with Arizona, so I'm going to draw an edge connecting them. Nevada also shares a border with Arizona right here, so I'll connect those. Nevada borders Utah. Utah then borders Colorado. Colorado borders New Mexico. And Utah borders Arizona. And Arizona borders New Mexico. So again, we did not say that because these meet at a corner, we're not going to say that Utah and New Mexico border each other. Okay, so here is a possible graph model for this scenario. So I've got my 6 states and then the common border represented by an edge. Now this graph can be drawn very differently and still represent the same graph model. What matters when you're looking at your graph model is the number of edges that you have connecting the correct vertices. So basically any graph that represents this scenario will have the same vertex set and the same edge list, but it might look a little bit differently drawn out on paper. Now there is a totally different graph model than this presented in your book. Now when I say totally different, I mean that they kind of squared things off and have it a little bit more geometric with triangles and rectangles. So yours could look like that, or it could look like this, or to maybe show you another way to do this that represents the same relationship. Maybe I'll put these vertices in a circle. Okay, so I'll have California, Nevada, Utah, Colorado, New Mexico, and Arizona. Okay, so I kind of have these in a circle, so now I'm just going to draw on their connections. So California, I want to connect that to Nevada and Arizona. Nevada is already connected to California, so I need to connect it still to Arizona and to Utah. So Utah, I need to connect to Colorado and to Arizona. Okay, so here's where you don't want your dot to get lost, so I'm going to make that a little bit bigger so it stands out. Alright, so then I just need to connect Colorado to New Mexico, and then New Mexico to Arizona. Okay, so if I'm going to argue that both of these graphs are the same graph, meaning they represent the same scenario, then I have to have the same vertex set, and I have to have the same edge list. So I'll leave it up to you to verify that these two represent the exact same scenario. So in this next graph model, we're going to use a graph to represent this floor plan. So each of these rooms have already been designated with a capital letter, and then O is going to represent outside. Alright, so I'm going to have A, B, E, D, C, and then maybe I'll put the outside one all the way out here. All right. So let's go ahead and draw in our connections. So A looks like it has two connections to outside. Okay, so it'll be one connection. That'll be two connections, so maybe I'll come in here. So every doorway is going to be a way to get from one location to the other. So this represents the two ways to get outside, and I've already drawn those in. And then looks like A is connected to B. It's connected to D. And it's connected to E. I'm going to move on to B next. So B has two connections to outside. B is connected to D, and B is connected to C. C has two connections to outside, and C is connected to D. D has one connection to the outside, and it's connected to E. And then finally, E looks like it has two connections to the outside. Alright, so let's bring these guys over here. And one more. Okay, so you might have drawn yours a little bit differently, but ultimately your graph model should have these 1, 2, 3, 4, 5, 6 vertices, and you have to have the same edge list if we were to go through and cite all these edges. Okay, and the next one, this is going to be a graph that we're going to draw that models what's going on in the subdivision. So for the subdivision, what's going to happen here is that every one of the intersections, and on this one I'm going to maybe come in with a slightly bigger marker. So over here I've given you kind of like a lighter version of the subdivision, just to help you visually see what's going to go on here. But on like any exams or assessments or anything like that, when you are asked to do the graph model, you can't do it on top of the picture I'm going to give you. You have to do it off to the side. So this one, I've just given you this lighter model just so we can kind of see what's going to go on, and so that way you can kind of see the spatial orientation. So what's going to happen is that every one of the intersections is going to end up being a vertex, and every one of these streets that goes from one intersection to the next intersection is going to be an edge. So meaning coming just maybe up here, these are going to be intersections, so those are going to be vertices, and then connecting them is going to be an edge. So there is actually two edges right here and three vertices across just this top region. Now when we're going through and talking about these edges, so for instance, maybe let's come up here. So there is no edge from E to C. There is a, and we're going to start this language in a little bit, but we are going to say there is a path from E to C, meaning from E to D and then D to C. But E to C does not have a direct connection. There's this pit stop right here. You're going to have to stop before you can go forward. So there's technically the two edges right here. The same thing is going to go on right here. So to get from this intersection to this intersection, you have to go through this intersection. So we're going to kind of consider that to be a pit stop. So then we're just going to come through here, and every one of these intersections is going to be a vertex. And then we're going to connect all the intersections. And we're going to do this for this entire neighborhood. Okay, so right here there's an intersection. Alright, we're just going to come through and draw in all of our edges so far. Alright, so then moving over here, let's see, there's this park right here, so we're going to have to go around this park. Alright, and then we got this bottom region down here. Oh, and there should have been one right there for that intersection. And let's see here. Yep, that's a street right there. And then one around the back side of the school. Alright, and that looks to be it. So there's where every intersection is a vertex and then every street as an edge.